Hi, in this video, I'm starting chapter 13, the basics of probability theory. That's this section is going to, I'm going to cover it in two parts. So the first thing to know is that probability measures likelihood. How likely is something to happen? Okay, we're going to read the introduction of the chapter. Okay, so they start with this situation. When you bought the tickets, you were looking for you were looking forward to a warm summer evening, enjoying a relaxing ball game with your friends. Instead, here you are, huddled under a poncho, waiting out a long rain delay. The weather report was wrong, and you wish you had bought your tickets for tomorrow's game instead. As we all know, predicting weather is not an exact science. The weather is an example of a random phenomenon. So random phenomena are occurrences that vary from day to day and case to case. In addition to the weather, rolling dice in Monopoly, drilling for oil, and driving your car are all examples of random phenomena. Although we never know exactly how a random phenomenon will turn out, we can often calculate a number called a probability that it will occur in a certain way. We will now begin to introduce some basic probability terminology. So new chapter, we're going to start with some definitions. The first definition is the definition of an experiment. An experiment is any observation of a random phenomenon. The different possible results of the experiment are called outcomes. And the third definition is the definition of a sample space. The set of all possible outcomes for an experiment is called a sample space. Okay, so usually when we start studying probability, one of the most simple examples is the experiment of flipping a coin. So one example that illustrates, one of the simple examples that can illustrate the three definitions above. If we observe the results of flipping a coin, we have an example of an experiment. So the experiment is going to be flipping the coin. The outcomes of this experiment are head and tail. And the sample space is going to be a set. We're going to bring back some of the set notation. So the sample space is, we're going to denote it with S, and it's going to be the set of all possible outcomes. So that's going to be a set. Okay, so let's do other examples. We are going to determine the sample space for each experiment. Again, the sample space is the set of all possible outcomes. That's example number 1. On page 660. So determine a sample space for each experiment. The first experiment is that we select an iPhone from a production line and determine whether it is defective. So the sample space, we're going to denote it with S. The outcomes of the sample space are going to be defective and non-defective. B. The second experiment, a food services worker at your school is being tested for 3 consecutive months for the coronavirus, and we know the results of these tests. The sample space, so we have 2 outcomes. The outcomes are positive and negative. That the employee has COVID or he doesn't. So the outcomes are positive and negative. Positive that we're going to denote with P, and negative that we're going to denote with N. The sample space, the sample space is going to be the set of all possible outcomes. So the first one, this is highly unlikely, but I guess it's a possibility that he tests positive, that he or she tests positive all 3 months. Again, I haven't heard of this happening. The second one is that this person tests positive for 2 consecutive months and negative for the next one. And that may happen if this person got tested at the end of 1 month and then got tested at the beginning of the next one. Another one is that this person tested positive, then negative, then positive. And the last possibility, when this person tested positive in the first month, is positive, negative, negative. And there are 4 more: negative, positive, positive, negative, positive, negative, 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 positive, and negative, negative, negative. So this is the sample space of this experiment. In part C, we select 1 card from a standard 52 card deck. And then without returning the card to the deck, we select a second card. We will assume the order in which we select the cards is important. So that's the experiment. Now the problem is that the sample space is too large. We know by now the fundamental counting principle, so we can use that, or you can see it as permutations. But the experiment has 52 times 51, so it has 2,652 outcomes. Okay, so it's going to be hard to write the sample space like we did the first 2. So I'm just going to write that the sample space is too large. The sample space is too large to write. ending, we roll 2 dice and observe the pair of numbers showing on the top faces. Okay, this one is not as bad as the previous one. I'm not going to write all the outcomes. This looks like a 5. I'm not going to write all the outcomes, just show a pattern. Okay, so to indicate the pattern, the outcomes can be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. The next one would be 2, 1. Well, I should write it. I should write 2, 1. So that would be 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so on. So the last ones are going to be 6, 5, and 6, 6. You remember set notation, the number of elements in this sample space is going to be 36. We learned how to count that by using the fundamental counting principle. The first die has 6 outcomes, the second one has 6 outcomes. So the total number of outcomes in this experiment is going to be 6 times 6. Okay, so we have been using sets to denote the sample space. So there's a relationship to sets. You can think of the sample space as the universal set, and each set of the universal set, or each set of the sample space, is going to be called an event. So I'm copying the definition of event from the book. In probability theory, an event is a subset of the sample space. Okay, so we're going to write events from the sample spaces in the first example. So that's on the same page. So we're going to write each event as a subset of the sample space. The first experiment, well, not the first experiment. The experiment is flipping the coin, and the event is that a head occurs when we flip a single coin. The sample space is head and tail. So the event, we're going to denote this with D. The event that a head occurs when we flip a single coin is going to be head. So referring to example 1B, the one with the coronavirus, only one negative result occurs when in the coronavirus testing. So let's look at that. In part B, so the event is going to be the set of outcomes in which only one negative result occurs. We can see that there are 3 of those. The set has 8 outcomes, but this particular event has 3 outcomes. And those are, if only one negative result occurs, those are positive, positive, negative, positive, negative, positive, and negative, positive, positive. So these are the 3 ways in which only one negative result can occur. And part C, a total of 5 occurs when we roll when we roll a pair of dice. So there are 4 ways to obtain a phi. 1, 4, 2, 3. And as we did before, we're assuming that that the dice are different colors. So the ways to obtain a 5 are 1, 4, 2, 3, 3, 2, and 4, 1. Okay, so we have an idea of the sample space that's related to sets. The sample space is going to be like the universal set, and an event will be like a subset of the universal set. So we will use notions of outcome, sample space, and event to compute probabilities. Intuitively, you may expect that when you roll a fair die, each number has the same chance, namely 1/6 of showing. In predicting weather, a forecaster may state that there's a 30% chance of rain tomorrow. You may believe that you have a 50-50 chance, that is 50% of getting a job offer in your field. In each of these examples, you have assigned a number between 0 and 1 to represent the likelihood that the outcome will occur. So you can interpret probability intuitively as in the diagram below. An event that has probability equal to 0 is going to be an impossible event. An event with probability of 1/2 has a 50-50 chance of occurring, and an event whose probability 1 is a certain event. The closer it is to 0, the least likely it is to occur, and the closer it is to 1, the more likely the event is to occur. So I'll copy the definition of the probability of an outcome and the probability of an event. That's page 662. The probability of an outcome in a sample space is a number between 0 and 1 inclusive. The sum of the probabilities of all outcomes in the sample space must be 1, and the probability of an event. So we're going to set up some notation. The probability of an event is written P of E, and is defined as the sum of the probabilities of the outcomes that make up E. So this stands for probability of event E. And we have the formula, the most basic formula for probability. This is called the empirical assignment of probabilities. Okay, if E is an event and we perform an experiment several times, then we estimate the probability of E as follows. The probability of event E is the number of times the event occurs over the number of times that the experiment is performed. This ratio is sometimes called the relative frequency of E. So just a few notes. A probability can be written as a decimal or fraction, but never as a percent. So as a decimal or as a fraction, but never as a percent. You can say that the probability is 1/2 that the probability is 0.5, but it's incorrect to say that the probability is 50%. It must be a number between 0 and 1. So we're doing example 3. So we're still on page 663. A pharmaceutical company is testing a new COVID-19 vaccine. The experiment is to inject a patient with the vaccine and observe the occurrence of side effects. Assume that we perform this experiment 100 times and obtain the information in table 13.1. And we have a table that summarizes the side effects. So 72 people had no side effects, 25 people had mild side effects, and 3 people had severe side effects. So based on table 31, if a physician injects a patient with this vaccine, what is the probability that the patient will develop severe side effects? Okay, so the probability, so the event E is the event that the patient develops severe side effects. So the probability of E is going to be the number of times severe side occurred Okay, so that's going to be the number of times severe side effects occurred over the number of times the experiment was performed. Okay, so I'll try to draw this line more straight. To make it look like a fraction. And that is, they performed this experiment 100 times. That is the experiment of 100 people. And 3 developed severe side effects. So the probability of it, the probability that the patient develops severe side effects, according to this observation, is 3 over 100 or 0.03. So both ways to write this are correct, but 3% is not correct. Saying that the probability is 3% is not correct. The next example is at the end of the section. So I'm doing numbers 29 and 31. I have that, and I'm going to copy, we're doing number 21 and number 29 and 31. So in exercises 29 to 32, a cookie is selected at random from a basket of Girl Scout cookies containing 16 Thin Mints, 28 Caramel Delights, 12 Shortbreads, and 24 Shout-Outs. Find the probability that the specified cookie is selected. Okay, so let's find first the probability that we select a Thin Mint. So we can see that, okay, so if we add them, There are 16 Thin Mints, 28 Caramel Delights, 12 Shortbreads, and 24 Shoutouts. So there's a total of 80 cookies. Among those, 16 are Thin Mints. So the probability of selecting a Thin Mint is 16 over 80. 16 over 80 or 1/5. So 1/5 is correct, or 0.2 is correct. And number 31, the probability of selecting a Caramel Delight or Shortbread. Okay, so you can see that there are 28 Caramel Delights and 12 Shortbreads. The probability of that, I'm typing this, the probability of selecting a Caramel Delight or Shortbread okay, it's going to be, there are 28 Caramel Delight and 40 Shortbreads. And sorry, 28 Caramel Delights and 12 Shortbreads, so that's a total of 40 out of 80. So this is 40 over 80 or 1/2. Or it really depends on what my MATLAB is asking you to, how my MATLAB is asking you to write the answer. If they ask you for a fraction, keep it as a fraction. Otherwise, if they ask you for a decimal or for a certain number of decimals, do that. Okay, example 4. So in this example, they don't give you the total number of elements or the total number of outcomes in the sample space, but you can figure this out. That's page 664. Table 13.2 summarizes the marital status of men and women in the United States between the ages 18 and 34 in a recent year. All numbers represent thousands. If we randomly pick a male, what is the probability that he's married but not separated? Okay, so we need to find the number of males. That's going to be, in this case, the sample space is going to be the set of males. So the number of males is going to be 9,740 plus 36 plus 1,621 plus 24,655. And there is a total of 36,052 males. The probability that this guy is married okay, so 20, let's see, so male, 9,740 are not married, and we're not counting separated people. So that's going to be 9,740 over 36,000, 52. That's going to be approximately 0.27. Okay, so the reason why we talked about why we spend all this time with counting is to be able to use our counting techniques to find probabilities. So let's read that. So another way we can determine probabilities is to use theoretical information, such as the counting formulas that we discussed in chapter 12, like the fundamental counting principle, permutations, and combinations. Okay, so equally likely events, that means that every event or every outcome has the same chance of occurring. That's not the one. So if E is an event in a sample space S with all equally likely outcomes, then the probability of E is given by the formula that the probability of E is the number of times E occurs over the number of times that S occurs. So in equally likely events, each outcome has the same chance of occurring, or the same probability of occurring. Okay, so some examples are flipping a coin. That's an equally likely event because the probability of head is 1/2, and the probability of tail is also 1/2. Another example is rolling a single die, rolling a fair die. The probability of each outcome is 1/6. And one more could be drawing names out of a hat from a group of 30 students, or letting a computer randomly select a homeowner from a list of, let's say, 1,000. So the probability of each is going to be 1/1,000. So that's what equally likely events look like. Every outcome has the same probability of occurring. And remember this notation: N of E is the number of elements in set E, and same with N of S. Okay, we're doing number 11. Example number 11, or problem number 11, in which we use the counting formulas. Okay, singers Enrique, Katie, Rihanna, and Bruno are performing a charity concert for World Hunger, and the order of appearance will be chosen randomly. We will represent the outcomes in the sample space as strings of letters such as ERBK or KERB. In other words, we have permutations of those letters. So how many elements are in this sample space? So the number of elements are they. The number of elements in this sample space is going to be the number of permutations of 4 elements from a set of 4. We learned how to do that in the previous section. That's 4 factorial divided by 4 minus 4 factorial. So 4 factorial is 24. 4 minus 4 is 0, but 0 factorial is 1. So there are 24 ways in which they can perform. In B, we are going to express the event Katie and Rihanna perform consecutively as a set. So we're going to call that event E. So the event E is the event that Katie and Rihanna perform consecutively. We're going to list the elements in this sample space or in this event. If we list the outcome, the first possibility is that they perform first. Let's say that Katie and Rihanna perform first, and then the next could be Enrique or Bruno and Enrique. That's if Katie starts and Rihanna is second. But also, Rihanna may be first, and Katie might be next. So the other two choices are Enrique and Bruno or Rihanna, Katie, Bruno, and Enrique. The next case scenario is that Katie and Rihanna perform second and first. If they do it in this order, let's say Katie second and Rihanna is third, then Enrique might be first and Bruno may be last, or Bruno may be first, then Katie and Rihanna, and Enrique last. Or if Rihanna is second and Katie third, the choices are ERKB and BRKE. And the last case scenario is that they are the last two. So that can happen also in 4 ways. If they are last, let's say that Katie and Rihanna, that Katie is third and Rihanna closes. So the first two may be Enrique and Bruno or Bruno and Enrique. Or if Katie is the last one and Rihanna is the next to last, that could be one choice is Enrique, Bruno, Katie and Rihanna, so Rihanna and Katie. Or Bruno, Enrique, Rihanna, and Katie. So at the end, this event has 12 elements or 12 outcomes. And what is the probability that Katie and Rihanna perform consecutively? We call that event E. And the sample space has 24 outcomes. So the probability of E is going to be 12 over 24. Okay, the last example I'm doing today is number 12. Okay, so number 12, that's the next problem. That's the problem next to the one we did. Let's suppose that we're flipping 4 coins. So outcomes in the sample space are represented by strings of H's and T's. And we're going to assume one more time that the 4 coins are different. Let's say we have a penny, a nickel, a dime, and a quarter. Just to make sure that the coins are different. So the first question is how many elements are in this sample space? Fundamental counting principle. The number of elements in the sample space. That's a problem we did before. So each coin, or there are 2 ways to flip a coin. So 4 coins can be flipped in 2 times 2 times 2 times 2, or 16 ways. So express the event that there are more heads than tails as a set. So more heads than tails, that could be 3 heads, 1 tail. Or 4 heads and no tail. Let's call that event E. So more heads than tail. That could be the first 3 heads, the last one is a tail. Or head, head, tail, head. Or head, tail, head, head. Or tail, head, head, head. And there's only one choice for 4 heads. It's going to be that the 4 are heads. Next, what is the probability that there are more heads than tails? So the number of elements in the sample space is 16. The number of elements in this event is 5. So the probability that there are more heads than tails is 5 over 16. So I'm just leave it as a fraction. If they ask you in the homework to write as a decimal, just do that. This was the way part C. And finally, what is the probability that there are an equal number of heads and tails? So in D, that can only happen in one way, that there are 2 heads and 2 tails. So this sample space will consist of the elements. Let's say one possibility is that, or one outcome is that the first 2 are heads, the next 2 are tails. Or head, tail, head, tail. Or head, tail, tail, head. And if the first one is a tail, the choices are tail, head, head, tail, tail, head, tail, head, or tail, tail, head, head. And finally, the probability that there are an equal number of heads and tails is going to be 6 over 16. You can count 16 outcomes in that event. So the probability of that there's an equal number of heads and tails is going to be 6 over 16. Or you can simplify this fraction as 3 over 8. So if they ask you to write a simplified fraction, leave it as a fraction. If they ask you to round to a decimal, write it as a decimal. So I will finish this section in the next video. Thank you for listening.